Welcome to the Deep Dive, the place where we transform stacks of specialized research into actionable, high-impact knowledge. If you've ever felt overwhelmed trying to keep up with material science, well, consider this your expert guide.
Happy to be guiding.
Today, we are undertaking a massive deep dive into a powerful, quiet technology that is impacting everything from aerospace insulation to next-generation solar cells. Sol gel-derived materials. The source material you provided is a fascinating collection of expert chapters from the Advances in Sol Gel-Derived Materials and Technologies series, backed by the International Sol Gel Society. It highlights how this chemistry acts as kind of a shortcut to creating tailor-made materials through processing routes that are often surprisingly inexpensive and, environmentally viable.
That's absolutely right. And what we're seeing in these chapters is the true maturity of sol gel technology. I mean, it's no longer just a lab curiosity. It really represents a powerful convergence, the careful use of chemistry, physics, and engineering to solve some of the biggest global challenges we face today.
A real toolkit.
Precisely. The material covers an extraordinary breadth, from fundamental processing control all the way to complex applications like advanced electronic materials, highly specialized sensors, effective photocatalysts for environmental cleanup, and robust energy storage solutions. Our mission today is to go through these chapters, extracting the most crucial and maybe surprising technical and application-focused insights for you.
Okay, let's start where the journey begins, the chemistry itself.
Right.
Sol gel processing. At its core, it's all about controlling the nanoarchitecture of a solid material, starting from a liquid phase. Before we get into the incredible properties of aerogels, maybe walk us through the essential steps. What's actually happening during that transformation from liquid to solid?
Okay. So the sol gel process is, well, it's a masterclass in controlled precipitation, really. You begin with the liquid colloidal suspension, the sol, which is essentially nanoparticles floating around in a solvent. The goal is to chemically bind these particles together to create a solid, continuous network, the wet gel structure. And the reason sol gel is so revolutionary is precisely the ease with which we can control this nanoarchitecture at, well, pretty much every single step.
So you're building it from the bottom up.
Exactly. And this process reliably breaks down into 4 core stages. The first is sol formation, and this is driven by 2 simultaneous chemical reactions, hydrolysis and polycondensation.
Okay, those sound pretty dense. Let's break down hydrolysis and polycondensation maybe with an analogy.
Good idea. Think of it like a microscopic construction project. You start with your precursor materials, typically silicon alkoxides like TOS, tetraethyl orthosilicate. Hydrolysis is the first chemical step. Water molecules come in, and they replace these easily displaced groups, the alkoxy groups on the precursor, with hydroxyl OH groups. You're essentially activating your building blocks.
Got it. Preparing the bricks.
Right. Then comes polycondensation. These activated hydroxyl-rich molecules start linking together, cross-linking, branching out, much like glue setting between those building blocks. This forms a 3-dimensional polymer network throughout the liquid.
And once that network starts taking over, spreading through the whole volume, we hit the second stage, gelation.
Correct. Gelation is simply the point where enough cross-linking has occurred that the polymer network spans the entire volume of the liquid. You end up with a system where the solid network kind of separates out from the solvent. It's a phase change, moving from a viscous liquid to a semi-rigid wet gel.
Now for the third stage, which the sources say is often lengthy, aging. Why is letting the wet gel just sit there in its mother solution so vital for the final material strength?
Aging. It's the mandatory structural reinforcement step. If you tried to dry the gel immediately after gelation, it would just be too weak, it would collapse. During aging, 2 critical things happen. Ostwald ripening and the polymerization actually continues. Small, less stable particles dissolve, and then they redeposit onto the neck regions. Those are the connection points between the larger polymer clusters. This coarsens the structure a bit, but crucially, it increases the mechanical strength and durability of the backbone. This helps preserve the final porosity we desperately want.
And here's that surprising detail the sources highlight. The time needed for optimal aging varies wildly. Silica alkoxide gels like those from TOS need a massive 48 hours for proper reinforcement. Yet some sodium silicate aerogels only need 3 hours. Why such a dramatic difference?
That difference speaks directly to the kinetics, the speed of the precursor chemistry. Silicon alkoxides, being these larger organic molecules, well, they require a much longer time for those secondary dissolution and reprecipitation reactions to really effectively reinforce the neck regions and build a stable, interconnected network. Sodium silicate, on the other hand, it's an inorganic salt. It often forms a more immediate and robust colloidal particle system, so the cross-linking and coarsening just happens much, much faster.
Yeah, and for industrial processes, 48 hours versus 3 hours. That's a huge factor in throughput and cost.
Absolutely huge.
Okay, that level of precise control is impressive, but all that careful work can be totally ruined by the final step, drying.
Oh, it's the critical juncture, make or break. If you just let the solvent evaporate normally, the liquid-vapor interface creates immense capillary pressure inside those tiny pores. Imagine trying to suck liquid out of a really weak microscopic soda straw. The sides just collapse inwards. The result of simple evaporation is what we call a zero gel, and it's characterized by massive shrinkage, typically 40% to 60%, and very low porosity.
So to achieve the miracle material, the aerogel, with its incredibly high porosity, we have to somehow eliminate that capillary pressure. What are the specialized methods?
Right. The classic method is supercritical drying, SCD. You basically heat the solvent above its critical temperature and pressure point. At that point, there's no longer a distinct liquid-vapor interface. The solvent leaves as a supercritical fluid, completely avoiding surface tension and capillary pressure. This method produces these amazing materials with porosities reaching up to 99% and densities down to, well, 84 kilograms per cubic meter. Incredibly light.
But probably expensive and complex to do at scale.
Exactly. So the more industrially palatable method, which is becoming increasingly viable, is ambient pressure drying, APD, or sometimes called subcritical drying. This requires a pretreatment step, though. Chemical surface modification using agents like TMCS, trimethylchlorosilane. This treatment chemically modifies the surface of the gel pores, makes them hydrophobic, water-repelling. This significantly mitigates those capillary stresses, allowing the structure to survive drying at normal atmospheric pressure without catastrophic collapse. Much cheaper, much easier to scale.
Let's pull back for a second and look at what controls the structure right from the very start, the catalysis. How does simply choosing an acid over a base catalyst profoundly change the final material?
The catalyst. It dictates the geometry of the polymers that form. Think of it as controlling the shape of the building blocks themselves. Under acidic conditions, low pH, hydrolysis is slow, but the polycondensation tends to be restricted to forming linear or weakly branched chains. This results in weak, low-density, coarse-textured gels, almost like long, stringy fibers. But interestingly, these often have a huge internal surface area.
Okay, and the opposite.
Conversely, basic conditions, high pH, promote extremely fast hydrolysis and lead to highly condensed, tightly cross-linked polymers that form dense, compact clusters. This results in high-density, fine-textured gels with closely packed particle arrays, stronger but less surface area.
So it sounds like researchers always have to make a trade-off, maybe between high surface area and mechanical density.
Traditionally, yes. Which is exactly why the breakthrough of two-step catalysis acid-base is so important. By starting with acid to control the hydrolysis rate, getting those longer chains maybe, and then transitioning to a base to accelerate and control the polycondensation and cross-linking, you get much finer tuning. This technique, combining the best of both worlds, has produced some of the highest quality materials recorded, including TEOS-based aerogels, even produced via the cheaper APD route that achieves surface areas exceeding 1,100 square meters per gram. That's the hallmark of total nanoarchitectural control.
Wow. And it's that precise control, that ability to build the structure almost atom by atom, that makes aerogels so useful across so many sectors, from incredibly light aerospace components to those ultra-efficient insulation materials we hear about. Okay, since we've established how sol gel chemistry lets us tailor the porosity of materials so well, let's pivot that knowledge toward light. Chapter 3 focuses on using sol gel to create functional thin film coatings.
How is this chemistry becoming the go-to technique for controlling optical properties like reflection and transmission?
Right, optics. The goal here is to precisely manage the speed and direction of light as it hits a surface, and the key knob we get to turn with sol gel is the material's refractive index. Sol gel is ideal because it allows us to tune the RI in two main ways: composition and porosity. And both of these are fundamentally controllable right from the liquid synthesis stage.
Let's start with composition then. What kind of mixing allows for RA tuning? How does that work? Well, we typically use a binary blend, mixing precursors for a high index material and a low index material. A classic pair is silicon dioxide, SiO2, that's the low index component, sitting around N-indole 1.45. And titanium dioxide, TiO2, that's the high index component, around N equal 2.2, maybe up to 2.4, depending on the form. By creating these hybrid inorganic networks, for instance, by carefully varying the city ratio in a mixed oxide film during the sol-gel process, you can continuously tailor the refractive index. The sources note you can reliably hit pretty much any point between 1.45 and 2.27. That dynamic range gives you tremendous design flexibility.
Okay, the second lever, porosity, that connects directly back to what we just discussed with aerogels, right?
Absolutely. It's the same principle. Because air has a refractive index of 1.0, introducing pores, empty space, drastically lowers the overall effective refractive index of the composite material. If you can achieve, say, 75% to 80% void volume in a silica film, you push the RI down to the very low values needed for things like anti-reflective coatings or ARCs.
Speaking of ARCs, the simple goal there is just maximizing light transmission into a substrate, like a camera lens or a photovoltaic panel, and minimizing reflection. Sol-gel facilitates two major ARC architectures, it seems.
Yes, exactly. The first is the gradient type ARC. This involves creating a layer where the RI decreases continuously, smoothly, from the high-index substrate like glass all the way down to the low-index air. This gradient is highly effective because it minimizes reflection across a broad range of wavelengths and also viewing angles. It's incredibly stable optically.
But I imagine creating a perfect continuous gradient must be quite difficult to manufacture consistently.
It is, yeah, and there's that engineering trade-off again. Achieving the necessary ultra-low RI right at the outer surface requires an extremely porous structure. And unfortunately, that translates directly into low mechanical durability, low scratch resistance. Researchers often resort to complex multi-layer stacks of AO2, TiO2 nanocomposites to try and manage this trade-off between optical perfection and physical toughness.
Okay, so what's the more robust, maybe more common industrial solution?
That would be the interference type ARC. This is generally easier to mass produce. It relies on the classic optical principle of using alternating layers of high RI and low RI materials. The thickness of each layer is precisely tuned, typically quarter wavelength thickness, so that the light waves reflecting off each interface interfere destructively, essentially canceling each other out. This strategy is commercially mature and used very widely in things like laser optics, camera lenses, and precision filters.
What I find most compelling, though, reading this chapter, is the move toward multifunctional coatings. Not just controlling reflection, but adding active features like self-cleaning properties.
Ah, yes. That's where sol-gel's flexibility really shines. Take photocatalysis, for example. Porous TiO2 films are excellent self-cleaning agents because TiO2 breaks down organic contaminants like grime or fingerprints when it's exposed to UV light like sunlight. The challenge is pure TiO2 has a high refractive index, which isn't great for an ARC, but sol-gel allows researchers to create ultra-porous titania films, sometimes with up to 80% porosity. This pushes the effective RI down significantly, making the film anti-reflective and photocatalytic at the same time, and they often add a dash of inert silica SiO2 into the mixture. This boosts the film's thermal and mechanical stability without really ruining the pore structure or the photocatalysis.
Smart. Moving beyond simple layers, sol-gel is also described as the essential tool for building photonic crystal structures that literally impose order on the flow of light itself.
Correct. These materials need periodicity, a repeating structure, at the scale of the light's wavelength. For the simplest type, 1D photonic crystals, often called Bragg reflectors, sol-gel is perfect. You simply use repeated liquid deposition techniques like spin coating or dip coating to build up alternating layers of high RI materials like titania and low RI materials like silica. This stack forms a filter that very strongly reflects specific colors or wavelengths while letting others pass through, useful for sensors or optical filters.
But the truly advanced materials are the 2D and especially 3D photonic crystals. How do you use a liquid chemical process to build structures with that kind of micron scale order in all three dimensions? That seems incredibly difficult.
That's where we often rely on biotemplating or nanoparticle self-assembly. For 3D photonic crystals, which are sometimes called opals or inverse opals, researchers use monodisperse spherical nanoparticles, things like polystyrene or PMMA beads, all exactly the same size, as a scaffold. These tiny spheres naturally pack themselves into a perfect 3D crystal lattice, like a microscopic stack of oranges.
So a microscopic egg carton structure.
Precisely. Then, the sol-gel material, often a high-index material like titania for maximum effect, is infiltrated into the gaps, the voids between the spheres. It flows in and fills all the space. Once the gel sets, the original polymer spheres are removed, usually by burning them out or dissolving them. What you're left with is a precise, porous replica of the original pack structure, an inverse opal. And if the refractive index of the sold gel material used is high enough, this inverse opal structure can possess a complete photonic band gap. This is the really incredible result you mentioned. A microscopic cage designed purely by chemistry that literally prevents light within a certain frequency range from traveling in any direction through the material. The conforming nature of the Sol-Gel fluid is pretty much the only way to achieve that level of precise, complex filling.
We've established how Sol-Gel is the master of controlling porosity. Now let's introduce nature's own masters of porous materials. Chapter 4 focuses on diatoms, these incredible microscopic algae with highly structured silica skeletons, and their emerging role in environmental applications.
Ah, diatoms. They are quite literally nature's most sophisticated nanofactories. They're unicellular algae that, just under mild aquatic conditions, manage to synthesize these highly ornate hierarchical biosilica cell walls called frustules. The precision and complexity of these structures, I mean, they look like tiny glass jewels under a microscope, have inspired an entire field of research in material science, biomimetics, and biotemplating.
Okay, so when we talk about leveraging diatoms for technology, are we using the diatom shells directly as they are, or are we mainly just copying their intricate structures?
We're doing both, actually. The two main paths are biotemplating and modification. Biotemplating is the copying process you mentioned. You use the pristine diatom frustal structure as sacrificial template. You infiltrate the structure with a sol-gel precursor for, say, TiO2 or maybe zinc sulfide, let it solidify. Then you carefully remove the original biosilica, often by dissolving it or burning it away at high temperature. What you're left with is a perfect structural replica of the diatom shell, but made of a different material, metal, semiconductor, whatever you chose. These replicas are being studied for applications in enhanced catalysis, light trapping in solar cells, and advanced energy storage because they inherit that amazing high surface area and intricate structure.
And the other approach?
The second and often simpler strategy is modification. This involves keeping the native biosilica frustule intact, but chemically altering its surface using sol-gel techniques or similar chemistry.
Right. Let's focus on how these modified diatoms are being used specifically to help clean up the environment. What are the key applications there?
The primary environmental uses discussed are photocatalysis and adsorption. For photocatalysis, diatoms act as incredible, naturally high surface area supports. Researchers coat the frustules with sol-gel-derived TiO2 nanoparticles using precursors like titanium isopropoxide. The unique architecture of the diatom doesn't just offer a massive surface area for the TiO2 to sit on, it can also help scatter and trap incoming light, enhancing the photocatalytic efficiency for degrading organic pollutants in water. Plus, the silica support often improves the thermal stability of the TiO2 nanoparticles.
Makes sense. And for adsorbent materials, basically mopping up toxins, how does modification play a role?
Right. This is where surface modification is absolutely vital. The native biosilica surface is pretty chemically inert. It doesn't grab onto much. So we use a sol-gel-inspired technique called silanization. This involves reacting the silica surface with organoalkoxysilanes, like 3-aminopropylfreethoxysilane, often abbreviated APTs. This process functionalizes the silica surface by adding specific chemical groups like amine groups from APTs that can act as molecular sensors or, crucially for cleanup, as highly effective chelating agents. These added groups can strongly bind to heavy metal ions like lead or cadmium, or they can capture specific toxic organic compounds, making the diatoms effective tools for bioremediation efforts.
So the sol-gel chemistry provides the specialized molecular hand or hook that grabs a specific pollutant, while the diatom itself provides the enormous pre-structured surface area to deploy those hooks.
That's a perfect analogy, precisely. And looking ahead, the research described in the chapter is pushing towards creating diatom factories, potentially genetically manipulating diatoms to enhance their ability to either sequester metals internally or maybe even take up nanoparticle precursors directly from their environment. Historically, the cost and the sheer yield of large-scale marine microalgae production were seen as major limitations. But recent data suggests that industrial production is becoming economically viable, which really gives credibility to continued research in this area. It might not be science fiction for too long.
The themes we've discussed so far, precision control over structure, high porosity, and importantly, low-temperature synthesis, which is good for sensitive components, all seem to make sol-gel chemistry ideally suited for fabricating high-performance sensors. Let's delve into Chapter 5. How exactly does integrating the sol-gel matrix enable better detection? And what are the two main ways the matrix functions in these sensors?
Right, sensors. The versatility of the sol gel matrix is really the secret weapon here. It generally serves one of two primary roles. In the first role, the sol gel-derived material itself acts as the active sensing element. A good example is a metal oxide film, maybe made by sol gel. It changes its electrical conductivity when specific gases absorb onto its surface. The material is the sensor. In the second and perhaps more common role, the sol gel matrix acts as an advanced protective scaffold or host. In this case, the matrix itself needs to be highly transparent, mechanically robust, and often biocompatible, especially for biological sensing. Researchers use this matrix to immobilize an optically or electrochemically active component, the transducer molecule, the thing that actually signals the presence of the target. The matrix protects this sensitive molecule from the harsh environment while still allowing the target analytes, the things you want to detect, to diffuse in and interact with it. Silica is very commonly used here, as are ore morsels.
Wait, you mentioned ormosils. We should probably unpack that term a bit. What exactly are they?
Good point. Ormosil stands for organically modified silicates. These are essentially hybrid sol gel materials where organic groups are chemically bonded directly into the inorganic silica backbone during the sol gel process. This hybrid approach gives the resulting sensor material the best of both worlds. You get the mechanical robustness and optical transparency of silica, but you also gain the flexibility, maybe hydrophobicity, or enhanced biocompatibility afforded by the specific organic components you choose to incorporate. It's really essential for applications like creating flexible sensors you can bend, or for safely encapsulating delicate biological molecules.
Okay, that makes sense. Let's move to some specific gas sensing examples from the chapter, starting with optical detection methods.
Sure. Optical gas sensors often rely on changes in fluorescence or absorbance. For oxygen sensing, a common approach is to use the sol gel film to immobilize certain transition metal complexes, like ruthenium polypyridyl complexes. These complexes glow, they fluoresce, when excited by light. But when oxygen molecules are present, they collide with the excited complex and quench its fluorescence, basically turning the light off. The degree of quenching, how much the light dims, directly correlates with the oxygen concentration. And by tailoring the sol gel matrix, say, by making it more porous or adjusting the ratio of precursor and water, you can fine-tune the sensor's sensitivity and response time.
Clever. And another optical example.
Another key one is carbon dioxide sensing. Researchers have used fluorescent dyes, like one called HPTS, incorporated into a hybrid TSMTE's sol gel matrix. Often, they enhance this further by adding titanium dioxide nanoparticles into the mix. These sensors have achieved really high sensitivity, allowing detection even well below standard atmospheric concentrations of CO2. That's crucial for things like environmental monitoring or controlling conditions in closed-loop systems like greenhouses or bioreactors.
Okay, switching gears to electrical detection. What about resistive gas sensors for common industrial hazards like ammonia or maybe hydrogen? How do they work?
These typically rely on surface chemistry changing the material's conductivity. We synthesize metal oxide nanofibers, things like zinc oxide, ZNO, or titanium dioxide, TiO2, often using a technique called sol gel electrospinning to get these long, thin fibers with high surface area. When, say, hydrogen gas is absorbed onto the surface of a TiO2 nanofiber, it reacts with oxygen species that are normally present on the surface. This reaction releases free electrons back into the semiconductor material. This dramatically changes the material's electrical conductivity, its resistance, and the magnitude of that change is proportional to the concentration of the gas. For P-type TiO2 films, the chapter mentions incredibly fast response times for hydrogen detection, sometimes as quick as just 2 seconds.
That speed is vital for safety applications. And what about the really delicate task of physiological sensing, measuring things inside the body or in biological samples?
Ah, yes. That's where biocompatibility and the protective nature of the matrix are absolutely key. For sensors designed to detect nitric oxide, NO, which is a very important signaling molecule in physiology, researchers have actually successfully encapsulated fragile biological materials, like the protein manganese myoglobin, within a protective, transparent silica sol gel matrix. The matrix does two things. It stabilizes the protein, but it also allows the small NO molecules to diffuse in and bind to it. The resulting changes in light absorption, which are characteristic of NO binding to myoglobin in a natural physiological buffer, can then be accurately monitored right through the transparent gel. The sol gel essentially creates a safe little house for the biological component without hindering its function.
That's really elegant. Now, the ultimate challenge seems to be creating a system that doesn't just detect one specific compound, but can somehow discriminate between a whole array of different chemicals simultaneously, like an artificial nose.
Exactly. That takes us to the development of advanced sensor arrays. The optoelectronic nose, mentioned in the chapter, is a fantastic example of this. It utilizes sol-gel-derived ormosyl matrices, those hybrid materials we discussed, that host multiple different chemically responsive dyes, all spotted onto an array. You might have metal-containing dyes, pH indicators, redox-sensitive salts, all side by side. When this array is exposed to an atmosphere containing various chemicals, each chemical vapor creates a unique pattern of colorimetric responses across the entire array of different dyes. This unique fingerprint pattern allows the system to discriminate between, in one study, 19 different toxic industrial chemicals, TX, within just 2 minutes. The sol-gel matrix is critical for keeping these dyes stable and spatially separate on the array.
Amazing. And this array approach works for detecting ions in solution, too.
Yes, absolutely. Sol-gel techniques allow for the grafting of highly selective receptor molecules onto the surface of mesoporous silica, which has a huge internal surface area. For detecting toxic mercury ions, Hg2+, in water, for instance, researchers grafted specific sodium receptor molecules onto the silica surface. The resulting material selectively changes color from yellow to red only when Hg2+ ions are present, illustrating really high precision and selectivity thanks to that tailored surface chemistry enabled by the sol-gel route. The chapter also notes a highly specific fluorescent sensor for nitrite, NO2, in natural waters, built on similar principles.
Finally, let's touch on basic pH sensing. Sol-gel seems to offer a way around traditional issues like stability and the indicator dye leaching out over time.
That's right. Sol-gel-derived films doped with indicator dyes like neutral red or phenol red have been used for optical pH sensing for a while. The key innovation highlighted is using hybrid precursors, for example, co-condensing TOs with something like phenyl triethoxysilane. This approach creates a denser, less porous hybrid matrix that effectively chemically locks the indicator dye molecules into the network structure, really solving that perennial problem of the dye slowly leaching out into the sample solution. The stability achieved can be remarkable, with some sensors reported to maintain stable performance for up to a year. Furthermore, the flexibility offered by these hybrid sol-gel films allows for the development of pH sensor arrays that can be rolled up or deformed, making them suitable for integration into complex systems or wearable devices.
Okay, let's pivot now to a massive industrial headache: corrosion. Chapter 7 deals with using sol-gel chemistry to address this multi-billion-dollar problem. Specifically, it targets the replacement of those highly toxic chromate conversion coatings, especially the ones used on aluminum alloys. And the goal isn't just to build a better barrier, but to create a coating that is environmentally friendly and, fascinatingly, self-healing.
Exactly. The focus here is almost entirely on aluminum alloys, particularly the widely used AA2024T3, which is crucial in aerospace where corrosion is a huge safety concern. The sol-gel coating has to perform two critical functions. First, it has to act as an effective, impermeable physical barrier, just like any good paint or coating. And second, it needs to provide active protection that actually responds when that barrier inevitably gets breached, say, by a scratch or impact.
Right, so focusing on the barrier function first, how does the sol-gel structure itself contribute?
Well, structure is everything for a barrier. We know sol-gel films are inherently porous to some degree. Researchers have found that generally, acid-catalyzed sol-gel systems tend to form tighter, more condensed films with lower overall pore volume compared to base-catalyzed ones. This makes for a better initial passive barrier against corrosive species like chloride ions. The performance can be further optimized by carefully tuning the density and also the hydrophobicity, the water-repelling nature of the polymer network. And this is done by adjusting the ratios of water and organic components in the initial precursor solution during the sol-gel synthesis.
Okay, but even the best passive barrier will eventually fail due to mechanical damage. That's where the self-healing aspect comes in. How does the sol-gel matrix manage to host and then utilize these self-healing agents?
The sol-gel matrix acts as an ideal microscopic reservoir or container, precisely because its porous structure can effectively trap molecules and ions within its network. The most studied and effective active inhibitors discussed in this chapter are rare earth metals with cerium salts, particularly cerium nitrate, CNO33, being the clear frontrunner for aluminum protection. The sol-gel matrix traps these cerium ions, essentially holding them immobile and dormant until corrosion actually initiates somewhere on the metal surface.
And what is the fascinating chemical trigger that suddenly releases the healing power of this trapped cerium? It sounds almost alive.
It's a beautifully elegant mechanism, and it's entirely pH dependent. When the aluminum alloy surface experiences localized corrosion, say at the bottom of a tiny scratch, the electrochemical reaction that occurs consumes oxygen and water. This consumption leads to a sharp, localized rise in pH right at that damaged site. It becomes alkaline. This elevated pH is the signal. It triggers the rapid hydrolysis and precipitation of the soluble ions that were stored in the gel matrix. They react with the hydroxide ions present and form insoluble cerium hydroxide, CeOH3.
So it precipitates out of solution right where it's needed?
Exactly. This precipitated hydroxide forms a dense, passive barrier right over the corrosion pit, and it serves a double purpose. It physically blocks the further diffusion of corrosive species like chloride down to the metal, and by forming the precipitate, it consumes hydroxide ions, lowering the local pH back down towards neutral, which inherently slows the entire cathodic corrosion reaction rate. The fact that the release and deposition are triggered specifically by the local environment created by the corrosion process itself makes it truly self-healing. This responsive mechanism has been confirmed using advanced techniques like ICP-MS, which can actually track the release of cerium ions from the coating under corrosive conditions.
That's incredible chemistry. But how do researchers ensure the cerium stays effectively trapped in the matrix for potentially months or years before a corrosion event happens? You don't want it just leaching out slowly over time.
That's a critical point, and it comes back to the design of the sol-gel matrix itself, often using those hybrid organosilanes we talked about. The matrix is engineered to be dense and highly cross-linked. This minimizes the passive diffusion and mobility of the trapped cerium ions when there's no trigger. By creating strong chemical bonds within the polymer network and controlling the pore size, you maximize the mechanical trapping effect, ensuring long-term stability and reservoir integrity until that specific local pH gradient is established at a damaged site.
Makes sense. The sources also emphasize that adding nanoparticles into the sol-gel coating is critical for performance. What roles do they play? Are they just fillers?
Oh, they're much more than just fillers. Nanoparticles provide basically a triple threat. They offer mechanical reinforcement, making the coating tougher, they improve the barrier function, and they can also act as sources of active inhibition themselves. Firstly, they act as pore blockers. By filling in some of the residual nanopores within the sol-gel film, they reduce the overall permeability, which is vital for the initial passive barrier function. Zirconia, ZrO2 nanoparticles, which are often synthesized via sol-gel methods themselves, are great examples of this pore blocking mechanism. Additionally, nanoparticles of materials like ceria, CEO2, or zinc oxide, ZNO, can act as secondary reservoirs for active corrosion inhibitors, slowly releasing protective ions themselves or synergizing with the cerium system. They add another layer of resilience and longevity to the coating.
Okay. We briefly touched on adding organic inhibitors like benzotriazole, BTAH, into these coatings. Are they comparable in performance to the cerium-based self-healing systems?
Generally, the chapter suggests no, not for the active healing part. Organic inhibitors like BTAH definitely do enhance the passive barrier properties of the coating, making it more resistant initially. However, they typically lack the crucial mobility and responsiveness that characterizes the cerium salt systems. The cerium system dynamically reacts to the localized electrochemical environment, specifically the pH change. The organic inhibitors are generally static. They contribute to the overall barrier strength, but they don't possess that active, autonomous seeking and sealing mechanism that defines true, triggered self-healing protection in response to damage.
All right, now we move squarely into the critical area of energy applications. Chapters 8 and 9 focus on how sol-gel chemistry is used to integrate two real superstar materials, graphene and titanium dioxide, TiO2, into devices ranging from batteries and supercapacitors to advanced solar cells. Starting with Chapter 8, why is sol-gel proving to be such a perfect vehicle for harnessing graphene's exceptional properties in these energy devices?
Well, graphene, as you know, is famous for its almost unbelievable properties. Incredibly high specific surface area, phenomenal electrical conductivity, great mechanical strength and stability. But the big challenge has always been incorporating it effectively and homogeneously into other materials, especially oxides, without it just clumping up. Sol-gel synthesis really excels here. Because it starts from a liquid phase, it allows us to mix the graphene precursors or derivatives like graphene oxide, a GO, or reduced graphene oxide, RGO, directly into the liquid precursor solution for the other component, say a metal oxide. This achieves a highly dispersed, homogeneous nanocomposite structure when the mixture gels and solidifies. You get graphene embedded nicely within the oxide matrix.
Okay, let's look at specific examples. How does this help in energy storage devices like supercapacitors?
In supercapacitors, you need massive surface area and excellent conductivity for rapid charge storage and release. The chapter mentions sol-gel synthesis of graphene composites. These showed excellent recyclability and a high specific capacitance, reported at 62.2 farads per gram for a 1.1 ratio. Here, the graphene provides that crucial conductive highway network and the enormous surface area needed for ions to access the ZNO rapidly.
And in solar cells, particularly the well-established dye-sensitized solar cells, PSSCs, TiO2 is the traditional semiconductor workhorse. How does adding graphene via sol-gel supercharge its performance?
Graphene plays a couple of key roles here. It doesn't just sit there passively. It provides an almost instantaneous electron transport pathway out of the PiO2. When researchers incorporate graphene into TiO2 photoanodes, sometimes using composites like N-doped TiO2 graphene prepared via sol-gel methods, they consistently see significant increases in the solar cell efficiency. The chapter cites up to 9.3% efficiency reported in some cases. This improvement seems to stem from two main factors. First, the graphene might enhance the amount of dye the TiO2 can absorb, capturing more light. And second, and critically, it dramatically decreases the electron transport time through the thick TiO2 layer. This means fewer electrons are lost to a recombination with the dye or the electrolyte before they reach the external circuit. More electrons collected equals higher efficiency.
That makes sense. And graphene can also help cut costs.
Yes, there's an economic benefit too. Graphene ES WCNT, single-walled carbon nanotube aerogels, which can also be synthesized via sol-gel routes, have shown great promise as low-cost, high-performance counter-electrodes in DSSCs. They can potentially replace the expensive platinum, PT traditionally used, without sacrificing overall cell efficiency.
This strategy of integrating graphene seems absolutely vital for some of the newer emerging solar technologies like perovskite solar cells as well.
Absolutely. Perovskite solar cells are known for their high efficiencies, but they rely heavily on highly efficient charge transport layers, sandwiching the perovskite absorber layer. Sol-gel is used here to create the electron transporting layers, often based on TiO2, but combined with graphene derivatives like reduced graphene oxide, RGO. The RGO provides a very efficient, low-energy conduction pathway for the photogenerated electrons to be extracted from the perovskite layer and transported to the electrode. This minimizes losses and leads to major boosts in device performance. One study mentioned achieved 15.6% efficiency using this precise sol-gel-mediated integration of RGO with TiO2.
And finally, before we leave graphene, we see that performance boost carrying over into Li-ion batteries as well.
Yes, definitely. The chapter highlights TiO2 graphene nanocomposites synthesized via sol-gel methods. These materials have achieved charge capacities roughly double that of using pure TiO2 alone as an electrode material. In lithium-ion batteries, TiO2 can act as an insertion material for lithium ions during charging and discharging. Adding graphene enhances this process significantly by providing both high surface area for a rapid ion movement between the electrolyte and the electrode, and also excellent electrical conductivity within the electrode itself. This facilitates much faster charge and discharge rates and improves overall capacity.
Okay, moving to Chapter 9, let's focus specifically on the other star material, titanium dioxide, TiO2. We already know it's a photocatalytic and energy workhorse, but why is sol-gel considered such an ideal synthesis route for producing high-quality TiO2?
TiO2 is interesting because it exists in three main crystal forms, or polymorphs: anatase, rutile, and brookite. And crucially, these different crystal structures have very different properties, especially for photocatalysis. Sol-gel processing, particularly the careful choice between using an alcohol-based route, starting with a metal alkoxide precursor like titanium isopropoxide, or an aqueous-based route, starting with an inorganic metal salt precursor like titanium tetrachloride, allows the researcher to steer the crystallization process towards forming the desired phase, or control the particle size and morphology.
And which of those phases is generally the most desired for environmental cleanup and energy applications?
Critically, for most of these applications, the anatase phase is superior. For photocatalysis, the crystalline phase is the function. It determines how well it works. Anatase is widely recognized as being far more photocatalytically active than the rutile phase. There are a couple of reasons for this. Anatase generally has a higher adsorption affinity for organic compounds, meaning the pollutants stick to its surface better. But perhaps most importantly, it exhibits a significantly lower electron-hole recombination rate compared to rutile.
Lower recombination meaning?
Meaning when UV light hits the TiO2 and creates an electron and a hole, a positive charge, these charge carriers have more time in anatase to actually migrate to the surface and react with pollutants or water molecules before they simply find each other and recombine, releasing useless heat. A lower recombination rate means that charge carriers are more available to do the desired chemical work, maximizing the photocatalytic efficiency.
Okay, so if anatase is so superior, why is stabilizing it mentioned as such a challenge in the chapter?
Because of the inherent stability problem. Anatase is actually only thermodynamically stable, or metastable, at room temperature. When you heat it up, typically in the range of 400 degrees C up to maybe 1200 degrees depending on various factors, it undergoes an irreversible phase transformation into the thermodynamically stable rutile phase. This instability really limits its use in applications that might require high-temperature processing or operation. A lot of sol-gel research on TiO2 is constantly being refined, often by introducing specific dopant elements into the structure or carefully controlling particle size and morphology during synthesis, specifically with the goal of stabilizing that superior anatase phase and retarding its undesirable transition into the less active rutile form at higher temperatures.
We're going to conclude our deep dive today by focusing on a specific, perhaps less famous, but highly important, high-performance ceramic material detailed in Chapter 10, lanthanum phosphate, LaMPO4. Now, this might seem a bit niche compared to graphene or TiO2, but its unique properties are crucial for applications involving extreme environments. What makes this material, especially when synthesized via sol-gel methods, so valuable?
Lanthanum phosphate, LaPO4, is highly valued primarily for its exceptional thermal stability and very low thermal conductivity, especially at extremely high temperatures. Sol-gel synthesis is essential here because it provides an effective and, importantly, environment-friendly aqueous route to achieve the high purity and, crucially, the specific particle morphology needed for optimal performance of this ceramic. The synthesis method described is typically an aqueous sol-gel process, specifically using a technique called precipitation peptization, which is then followed by electrostatic stabilization of the resulting colloid. This is actually quite a complex multi-step method specifically designed to ensure the stability of the intermediate particles.
Okay, you mentioned precipitation peptization. Can you explain that a bit more? Why is that specific, slightly complex technique required for LiPo4?
Sure. When you initially precipitate the lanthanum phosphate from solution, you get a solid, but it tends to clump together, aggregate uncontrollably. Peptization is the subsequent step where you add a specific chemical agent, often an acid or a base, to break up these clumps and redisperse the solid particles into a stable colloidal suspension, a sol. This careful, controlled route produces very fine-sized primary particles, and importantly, they have a unique characteristic morphology. They are elongated, sometimes described as very long nanorods. The chapter mentions them being around 110 nanometers long right after the initial precipitation step.
Interesting shape. And similar to TiO2, this ceramic also undergoes structural transitions upon heating.
It does, yes. But its final high-temperature state is immensely robust. LaPO4 typically starts out in a hydrated form after synthesis. Upon heating, it transitions to an intermediate hexagonal crystal phase around 400 degrees C. Then, as you heat it further, it converts completely into its final thermodynamically stable monoclinic phase by about 1200 degrees C. And it's this monoclinic phase that's so valuable.
Right.
It's reported to be stable well above 1900 degrees C, and it possesses incredibly low thermal conductivity. The chapter quotes just 1.30 watts per meter Kelvin at a 1000 degrees C. That makes it an excellent candidate for high-temperature thermal insulation or barrier coatings.
And the processing benefits derived from using the sol-gel route are also huge for ceramics, right? It's not just about the final properties.
Yeah. Oh, massive benefits. Because the sol-gel-derived lamp-held powders consist of these very fine, nano-sized homogeneous particles, they enable what's called low-temperature sinterability. Sintering is the process of heating the powder compact to make it dense and strong. For LaMPO4 made by sol-gel, full densification can be achieved at temperatures as low as 1300 degrees Celsius. For ceramics processing, that is revolutionary. Conventional methods, starting with coarser powders, require much, much higher sintering temperatures, often exceeding 1600 or 1700 degrees C. So the sol gel route saves tremendous energy costs during manufacturing and also makes the material compatible with co-firing with substrates that simply couldn't handle those higher thermal loads.
That's a big deal. The most surprising application mentioned in the chapter, however, relates to its interaction or lack thereof with molten metals.
Yes, this is perhaps its most specialized and unique utility. LaPio 4 demonstrates remarkable non-reactivity and non-wettability with many molten metals, particularly non-ferrous ones. The chapter describes tests where sintered disks of LaPio 4 were exposed to molten metallic silver. The silver exhibited a contact angle greater than 125 degrees on the ceramic surface. High contact angles like that mean the liquid metal beads up, it doesn't spread out or wet the surface. This property makes sol gel-derived LaPio 4 powders ideal candidates for developing advanced mold release coatings or even entire crucibles for precision metal casting operations, especially where contamination of the melt must be absolutely avoided and clean separation after solidification is critical.
And that characteristic nanorod morphology we talked about earlier actually contributes to this non-wetting behavior, correct?
Absolutely. The elongated nanorod shape of the primary particles, when packed together, creates a naturally rough surface texture at the microscopic level. This inherent roughness, often referred to as contributing to the lotus effect, is critical. It significantly enhances the material's intrinsic hydrophobicity and contributes strongly to its non-wetting characteristics with liquids, including molten metals. This further suggests broader potential applications in developing non-stick or protective, easily cleanable surface coatings. #tag outro by.
Wow. We have covered a staggering amount of ground in this deep dive. We started with the basic 4 steps to transform a simple liquid chemical solution into a highly structured solid material. We explored how that precision allows us to build almost invisible coatings that can actually mold the flow of light. And we saw how this chemistry can be used to create smart, self-healing industrial coatings that fight corrosion and even engineer incredibly stable ceramics designed for extreme heat environments.
Yeah, the powerful takeaway here, I think the theme that really links all these diverse chapters together, is that the sol gel process is truly an unparalleled toolkit for advanced material engineering. It gives researchers this remarkable ability to precisely, and often relatively inexpensively, tailor the nanoarchitecture of a material, whether it's controlling porosity, tuning refractive index, engineering chemical reactivity on a surface, or enhancing thermal stability, simply by carefully controlling the solution chemistry, the choice of precursors, the catalysts, the aging conditions, right through to that critical final drying technique.
So this technology isn't just about creating new substances. It's really about integrating multiple, often complex functions into a single material system.
Exactly. That seems to be the future trajectory. It lies in creating these complex hybrid systems where inorganic backbones are seamlessly integrated with functional organic groups, or where intricate biological structures like diatom shells are used as precise scaffolds for new materials. And sol gel provides the flexible, often low-temperature, highly controllable synthetic route that's necessary to make these sophisticated multifunctional materials a practical reality.
Okay, so you, our listener, now have an extensive overview of how sol gel chemistry is actively disrupting fields like energy generation and storage, environmental remediation, advanced optics, and industrial protection.
Right. However, as often discussed in these chapters, the biggest hurdle for researchers frequently remains scaling these elegant lab-level breakthroughs up to massive, cost-effective industrial deployment. So given the fundamental control offered by sol gel synthesis and its proven ability to create these tailor-made porous materials with specific functions, here's a provocative thought for you to consider. What current industrial challenge, maybe in areas we haven't even touched on, like advanced filtration for water or air, or perhaps large-scale food preservation technologies, areas unrelated to energy or electronics, do you think is most ripe for disruption by mass-produced, tailor-made, porous, sol gel-derived materials?
That's a great question to ponder. We look forward to hearing your thoughts on that challenge. Thank you for joining us for this deep dive into the fascinating world of functional sol gel materials. We'll see you next time.